radar hack. I've never even heard of a radar hack.
I was shooting too straight. Permaban. Permaban for literally no reason.
Bro, call it shame, bro. Chill, bro. It's not what it looks like, I swear. I just got permaban.
The most popular one of them all, Call of Shame. Deplorable, horribly sexist, homophobic. Like, there's no proof. There's none.
What percentage of big streamers do you think do cheat? Zero. Less than zero.
There is nothing wrong with me cheating. Tell me one thing wrong. What is wrong with me cheating? Be completely honest. Like, if I'm hacking, you guys don't care. I just got permaban.
Bro, I just got banned, damn.
I've often claimed in many of my videos that skill-based damage exists in Call of Duty. I completely understand why this mechanic is in the game. It's designed to enhance the experience for new players, allowing them to benefit from skill-based hit detection. This makes the game more enjoyable for them. That being said, I completely disagree with it. In the past, whitelisted streamers were given this advantage, dating as far back to Verdansk. Streamers like Tim the Tatman, Swag, and Huskers had accounts set up by Activision to exploit this feature. They were essentially given the same perks that new players receive, allowing them to drop enemies with only a few bullets, benefit from a massive dose of extra aim assist, and anyone that shot them would be nerfed. They also benefit from very easy lobbies. If you shot one of these streamers, your first 6 bullets wouldn't even register. It was a deliberate way to make them appear better than they actually were, helping to maintain player retention during the pandemic and the early days of Warzone. But let's be clear, they were all frauds. Since then, many streamers have been removed from these white lists. As a result, they quickly turned to cheats to maintain their gameplay standards. Nadia and Symphony are prime examples of this, particularly during the Caldera era. However, things changed with Black Ops 6. I now have evidence that skill-based hit detection still exists. Additionally, streamers using Streamer Mode Plus continue to have this feature enabled on their accounts. Frauds like Modern Warzone and True Game Data continue to deceive the community to protect Activision's patent. They act as an extension of Activision's propaganda. I refuse to let these Warzone streamers mislead anyone. And now, I will present proof that skill-based hit detection is real in Call of Duty.
New players and some streamers in Call of Duty often receive targeted assistance to help them acclimate and improve their gaming experience. This assistance is part of the personalized player engagement strategies powered by tools like AWS Personalize. Some players receive the following: stronger aim assist to make aiming and tracking enemies easier. This helps new players feel successful in combat and maintain engagement. They also benefit from hit detection forgiveness. They get a slightly enlarged hitbox or forgiving server-side hit registration. This allows for near misses to count as hits, which can be crucial for maintaining confidence. Weapons assigned to new players might have reduced recoil, smoother handling, or less bullet spread. This encourages experimentation with weapons and reduces frustration. In some cases, new players might deal slightly more damage or have their damage output normalized. This levels the playing field against experienced players in early matches. Some players may take slightly less damage or regenerate health faster in specific situations, as this provides more time to learn and adapt to combat. Some game systems dynamically adjust difficulty or match conditions in real time. This ensures that new players aren't overwhelmed in their first matches. Matchmaking might place new players on teams with stronger teammates or in less pivotal roles. This reduces pressure and allows them to focus on learning mechanics. Now, let's take a look at the Activision pitch as they approach the launch of Warzone.
Good morning, everyone. I know you're here today to hear about how Call of Duty uses machine learning to personalize player engagement. And we're going to get into the details of that. But first, I want to tell you how we got here. Just like many of you in the audience, we have a product. In our case, our product is a video game, Call of Duty. And our product has a lot of unique features. Our game studios spend months building those features And we are very excited to talk about them. But first, we have to figure out what we want to talk about. And in the past, it might have gone something like this: a group of people sitting around a table, and someone says, you know what, we should talk about multiplayer. Players like playing together, and we've got some cool stuff this year. And people will nod their head, and then another group or another person at the table will say, you know what, but we should talk about zombies. Players love killing zombies. We need to make sure we include that. And then somebody else will raise their hand and say, don't forget, this year we have a new game mode. It's called Blackout. And this is our take on Battle Royale. Everybody's going to want to hear about that. And this will go on and on for some time. People talking about the different features in the game, trying to figure out what to focus on, until somebody asks that question. Okay, what are we going to talk about? What should we focus on? With so many features in our game, the correct answer is all of it. Our game studios build games to be inclusive. They want everybody to find something to enjoy in our game, just like you want your customers to find something that they connect to in your product. So how do we do that? Well, if we were a small gaming company, maybe we had 100 players, we could go to each one of them, we could ask them questions about what's important to them, what they're looking for in a game, and tell them how our product matches their expectations. Unfortunately, that doesn't scale. We needed a solution that's going to work for millions and millions of players. So how do we do that? That was with personalization. First, we started with rules. We would say, if you play multiplayer, we're going to talk to you about multiplayer. If you play zombies, you like hunting zombies, we're going to talk to you about zombies. And then we moved to machine learning. And today, we're going to talk to you about how you can use machine learning to drive personalization to connect your customers to features in your product. So first, let me just introduce ourselves. So we are with Activision, as you all know, mentioned already, we make video games. I am Gina Hope. I lead the consumer technology team. With me today is Mike Blesky. He leads our DevOps in infrastructure, and Diego Toledo, one of our software architects. So what is consumer technology? Let me be clear. We don't build games. We've got game studios to do that. Our job is to elevate those features and that content in the games and connect it to the players, finding those things that are most relevant to the player regardless of what channel they're in. That might be on one of our websites. That might be through in-game messaging. Could be in our mobile companion experience or in a voice skill. I've talked a little bit about features and connecting into players, but let's first take a glimpse at what those features might look like in our game. So here's a quick peek at Call of Duty Modern Warfare.
The rules of engagement have changed.
Stand clear! All stations on my mark. 3, 2, 1.
Going dark.
Go, go, go!
What's the plan? Shock and awe. That'll get their attention.
This is crazy.
Get down!
Yeah, but we're all a little crazy, aren't we?
Just take the gloves off and fight.
We gotta move now.
You want the gloves off? They're off.
As you can see, there's a lot to talk about in that game. A lot of features and a lot of different things that we could focus on. So how are we going to find the right feature for the right player? And how are we going to implement this machine learning approach for our players? Well, first we asked ourselves the question, What are we trying to solve for? What is our goal? What are our goals with this application? So we came up with a few. First, it's to deliver the right message to the right player at the right time and the right channel. We want to make sure that our players are playing the things in the game that they love, but we're also telling them about new areas that they may not have considered, something else that they may be interested in. We want to make sure that we're listening to the players. It's not good enough for us to make assumptions or go with our gut about what the players want to hear. We need to make sure we're taking their feedback seriously. We also need to do this while maintaining cost. And then finally, a system like this can be very complex and unwieldy. So we need to make sure whatever our solution is, we have a plan to handle it. So our solution focuses on 3 things. 1, less human intervention. Stop letting people define rules to choose what players want to see. And I'll tell you, this was probably the hardest for most people to give up. This means we can no longer go with our gut on what we think is important. We're letting the machine choose for us. And if we're going to let the machine choose, we need to give it lots of options. We need to have a variety of messages, different layouts, and channels. I may like a lot of text. Somebody else may want to see it visually. This person over here wants a video. And then we need to make sure we're continuously learning. We don't build it and set it and forget it. We constantly look at the model and see, is there a better way? Is there something we can tune to do differently? Are there better messages that we could be choosing? And now Diego is going to actually take us through the details of what that model looks like.
Okay, so let's talk about our machine learning solution. So what we're asking ourselves is, what is the best next message? This is really important, because what is the best next message that is going to lead to long-term engagement? Think that you guys might have teams that come to you and ask, okay, we need to increase engagement, we need to increase revenue, or we need to increase visibility for a specific game feature, and now you're juggling all those balls in the air, and you have like a finite amount of real estate inside of the game, right? So how do you deal with all of that? And you also sometimes want to make suggestions to the user. Try this different game mode, try this weapon, buy this new item. When is the right time to approach the user and make those suggestions? And the game is always evolving. And a message that is talking about a specific game feature in the past might become really relevant again because this new feature got revamped now. And now this old message needs to reprioritize. How do you go back and reprioritize things dynamically? Or maybe this other feature is broken and we need to deprioritize this really fast. How do we deal with that in real time? So for people that worked with live products, this curve is really familiar. So you have early engagement building up, and there's a peak, and eventually there's a tail. Now, different people are going to have different shapes. Some people are going to have like a higher peak, lower peak, shorter tail, longer tail, but that's what the average curve looks like. Now, another way to look into this curve is, this is your Call of Duty journey. Every part in this curve is what we were doing at that specific time. So every point in this red line is your state in your journey. So here, in the beginning, you are learning about a specific game feature. You're learning that you like this game mode. You learn that you like this other game mode even better. This is your preferred weapon. And it goes up, up, up. And then you start playing less and less and less and less. Now, different people have different shapes. But those shapes might overlap. And when those shapes overlap, we have people sharing states for a moment in time. So I can look at somebody that was in your state that you are right now, but this person was 6 months ago, and see what happened to this person. Did this person increase engagement, decrease engagement? What message this person was sent? And was it good, was it bad? Now, I get all this information, and I can make a decision about what to do with you right now. And this is really powerful because everybody, very different players, are helping each other, and we're going to have like a better product because of this. Now, the way we achieve that is through reinforcement learning. This is a textbook example of how classic reinforcement learning works. So I'm going to go really fast so you guys have like some background how everything was done. So in this grid, and generally you have like a reward state, which is the 1.0 on the top. And sometimes I have like a negative reward state, which for you could be the churn state. You want to avoid this state. And in reinforcement learning, what we're doing is we're trying to find the value of those other cells. Those other cells are specific states that exist in this world. And in this specific world, we have 4 actions. You can go up, down, right, and left. And we're trying to learn what is the value of taking this action in the specific state. What is going to give you that? So when you solve the world using reinforcement learning, you get something like this. You see that going up in different states have different returns, but if I drop you anywhere in this grid, you know where to go to find a reward. Now, how does it translate to Call of Duty? States for us is user attributes. So anything about engagement, revenue, preferred items, inventory, everything comes down to build your state. Every circle you see in the screen, it's a state. So the X's are churn states, the blues and the greens are states that I'm going to talk about it, but the arrows here are different because remember the arrows are the actions. It's how I walk from one state to the other. And messages are pretty much what we send to the user. So if I want to move a user from state 1 to state 2, I send him a message. Hey, do this in the game. Hey, try that. Hey, did you hear about this new game event? And by doing that, I change your state. I send it to another state. And some states are better than others. So a quick example. Let's imagine that somebody comes to you and say, hey, let's make everybody play zombies. Now, state 1, in this case, could be a state that is the user is a beginner, doesn't know much about Call of Duty, doesn't know how to find its way around the game. If we introduce this feature really early, it can lead to a low engaging state, which you see going down from S1. Now, what our model does is it's going to look ahead in the future and see, is there a better place that I can introduce this feature that is going to lead to a higher engagement? So in this, you can see there's a path. I need to reroute user to state 2 and state 3, and there, if I send him the same message, it's going to lead to higher engagement. Now, there's a risk. In state 2, the user can churn. You could churn from any state, actually. Now, how confident am I, the model, that I'm going to be able to avoid this state, and I'm going to make people go to state 3 in order to experience this feature? As long as I have a higher confidence, I'm going to do this rerouting. If I have a lower confidence, it's going to do something different. Now, messages are our arrows here. And we do have seasonal content, and we have evergreen content. Every time somebody adds a new message in the system, what you're doing, you're creating new arrows. So if the arrow that takes you from state 1 to state 2 is a seasonal content, a seasonal message that's going to be taken down tonight, that street got closed. You cannot send users there anymore. So this changed the whole strategy. And we're able to adapt that in real time. But you can do the other way around, too. I can go to somebody that generates content and says, hey, we should focus on taking people from state 1 and state 3. We should craft a message specific for that. So we can avoid the states 2 and avoid the churn state. You probably start to realize that our actual problem is much more complicated than the classic reinforcement learning problem. Because we have so many states. We actually have hundreds of thousands of states to explore. And we were learning in that previous example the value of taking an action in a specific state. And when you have like hundreds of messages and hundreds of thousands of states, there's no way you can explore all those pairs and learn the value of each one of them. It's too much stuff to explore. And as the game evolves, we have new states getting created. So for example, if you had a new feature, a new game mode, or something different that we want to track about the user, this translates to new green cells being popped into existence. And things get way more complicated now because now you have all those new states to be tracked. And the same thing for message, like I said before, messages are being created, deleted, removed, and edited all the time. And this changed the effectiveness of the message too. This is how this is the very center of the graph. We cannot fit all the hundreds of thousands of states here, but this is the really beginning. The lighter the color is, the more engaged the user is with Call of Duty. The size of the circles there is how many people are in that specific state. So you can see already some patterns that some states are connected to some other states. And this is really powerful now because I can give a heads up before somebody goes to like a critical churn state 1 week before. You can run simulations to see where people are going to be 1 week from now, 1 month from now, because we are learning here like how the world is connected and how user experience your game in the long term. So in the very center, you see a larger circle, and this is the root state. When you start playing Call of Duty, that's where you start. Now, because it's really dark, now it's dark because you start a game, we don't know anything about you. So everything about you is 0. So that's why it's a dark color there. But you see all those possible directions to go. There's all those possible futures for you to explore, and all those possible paths and where they send you to. Here you can see that it's clear that there's like a cluster with light circles on the bottom. You want to reroute users there. So that's the strategy that the graph is going to do. Okay, so it's really complicated because users could be in any state, and they have all those dynamic factors that I talked before. How do we navigate that? How do we find which state I want to send the user to? What is the best path for me to send the user? What we use is Monte-Carlo tree search. Monte-Carlo tree search really helps us with that. Because we don't have to come up with like a player model. Like we don't have to come and say, here's how the player is going to behave, here's how players think, here how messages work, this message is going to be tagged with that. We don't have to do any of that because we're going to approximate the word through sampling. And the more we sample, the closer we get to the real world. And we have enough traffic in Call of Duty. So we can actually approximate a very good model in a couple of hours. And this is designed for a big search space. You guys are probably thinking, oh, you guys have like so many different paths, so many different states. Monte-Carlo tree search really can deal with that. If you guys are familiar with AlphaGo, their search space was much bigger than our search space. So I'm not at all worried about the number of states that we have. And this deals well with noise. In noise, it's important because you're sending marketing content to the users, and not necessarily somebody did something because you told them to do it. Maybe their friend called them to do it. Maybe they saw an ad on YouTube, and they did that all along. Now, we need to be able to account for all this noise in the system and maybe make a U-turn about something that we just learned that was like a statistical fluke all along. Here's a quick review how Monte-Carlo tree search works. So we have those 4 distinct phases: selection, expansion, simulation, backpropagation. So in selection, you're in a state, and then we're going to look ahead and see where do you want to send this user to. So this is the path that we're navigating. Some paths are better than other paths, and so we're going to explore only the good paths. Eventually, you're going to reach a state that you don't know much about it. There's a leaf node, and that's where you're going to have the expansion and simulation comes in, because you want to know what happens when I do something in the leaf node. And backpropagation is the backpropagation of this value all the way up to the root. Now, you're going to propagate a +1, a -1. You're going to propagate a signal that next time you're in that situation, then you need to choose, you're in this state again, you need to choose a message. You know that you should explore this path or not. Now, look on the backpropagation side. You see that one side of the tree is being explored more than the other side of the tree. This is by design because remember that we don't want to explore every single part of the tree. It's just not feasible. So we're only looking for promising areas of the graph. But we could have an example that we have like an early reward of +1, +1, +1, which makes us explore one side of the tree more than the other. But if we were to avoid and explore 3 levels of no reward, probably there was like a +100 there somewhere. So we need to balance this exploration and exploitation. And this is the formula, the standard formula of Monte-Carlo tree search for exploration and exploitation. So in one side, you see in the left side, that's the reward. So this is how much I know about the subtree. This is how much I know about this path. I collected this reward, I collected this signal. I know that if I go here again, I'm going to get the reward. The other side is the interesting side, but what you need to focus here is the big N and the small n. The big N is every time my parent node was in a situation they had to choose between me and my sibling nodes, how many times my parent was in this situation. Every time this happens, you get a +1 on big N. Small n is every time I got selected when that situation happened. So what's happening here? Every time I got selected, small n grows. If the denominator grows, the fraction gets smaller and smaller, so it translates to that I become less attractive for next time I'm being looked into. And because I'm becoming less attractive, my sibling nodes are becoming more attractive because their small n stays the same because I'm being selected all the time, and their small n is just growing. Their numerator is growing, 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 growing. So they're becoming way more attractive now for the parent node. Select. Now, eventually, you're going to collect enough information. You know that there's no hope, this path is not good, you're going to get out of this up and down, up and down, up and down. You just want to converge to like an optimal path. That's what the log is doing here in the square root. This is just going to cap the value, so it's not going to grow much more than a certain number. And so in the end, after you explore enough times, the exploitation value is just going to dominate this side of the equation. Now, you might have a product, a business case that you do need to favor a little bit more or even much less exploration because maybe there's a penalty for you to exploring too much. Or maybe there's no penalty for you to explore. So that's the C, that's the constant, and you just play with C. There's a hyperparameter, and you choose bigger or smaller C's just to tune how much you want the model to explore. Now, until now, we talked about how to choose the next state. I'm in state 1, should I go to state 2, or should I go to state 4? So this is, we know how to do that. We're gonna look at the backpropagation values, and we see which states are better than other states. Now, how do I get to state 2? Remember, we need to choose a message. We have a huge catalog of messages to choose from, and showing a message to a user not necessarily is going to take to the state 2. Maybe it's going to take to state 5 or state 10, and some messages are better than others to take to state 2, which is the one I want to do. Now remember that we don't have a deterministic outcome. Not necessarily because I show you this message and you move state, it was because of me, and sometimes I need to show you the same message 100 times for this message to take effect. And the value might change over time because something is really hot now, there's a lot of buzz around this new feature, so this message is really affecting moving people to the specific state, but later the buzz goes down, so this message effectiveness goes down, so we need to be able to dynamically adapt to all those fluctuations. So we're running on an attribution model. Every time a user sees a message, we send to Kinesis Analytics. And every time a user changes states, we send to Kinesis Analytics. So we have those two tables. This is very simplified. Event table, you can think of like a state change event. And what we're going to do here, we're going to join by user IDs and timestamp. So we have this event ID there, and the event just happened. Now we're going to look through a window of time before this event happened. X minutes, X hours, X days, whatever makes sense for you, and see all the content the user saw before changing states. And then we're going to attribute the state change to that specific messages. So most of the time are going to be multiple messages. But most of the times, what is going to happen is the dark gray. And the dark gray is you're going to see a message, nothing happens. This translates to a self loop in the graph. And those are our successes and our failures. And later it's gonna, those successes and failures are we're gonna be used to determine how effective this message is in sending to a specific state. And from here, that's how the whole tree, how the whole graph gets built. Now, we're all in Vegas, right? So Thompson sampling is gonna help us find the true value of the message. And Thompson sampling is something that it was originally taught for slot machines in Vegas. And just let's think about an example right now that I come to you and say, we're gonna play tonight slot machines and we're gonna try to make as much money as we can, but we only have one night, finite horizon, very important. And the second piece of information is different slot machines have different payouts. So what we're doing here is we need to play in a bunch of slot machines try to approximate what is the real payout of those machines, and then for the rest of the night, only play that machine. So what we're doing here is the trial. The trial is every time the server was asked, give me a message for this user, and the server is going to see what's the best message, and it's going to learn. So in the beginning, you don't know much about what's the true value of those messages. On the top, you'll see the true value because you can go back in time and aggregate everything nicely, but at the time, we did not know. So every message is being explored equally, but you see that very fast. For example, number 3, we learned that message is crap. We cannot use that message anymore. So it just stopped exploring that message. So you can think of this as like a A/B test on steroids that we're shutting down bad variants on the fly, and we just double down resources on good variants. You see that green really is getting a lot of the traffic there, but we do still explore some of the other message, because remember, there could be a statistical fluke. It could just be living in a universe that you get 100 heads in a row, but the coin happens to be fair, so you need to always be able to make a sanity check. This is the same from before. Now, we're just taking different snapshots at different trial numbers. In the beginning, you don't know anything about any message. So any message has an equal probability between 0 and 100 from making a transition. So it's the same as random. Every message is random. Now, as some feedback start to come back, you start to see that you start to learn some curves here. You start to see that some probabilities. And very fast, you see green moving to the right and get skinnier and taller. So what happens here is that green is skinny and tall because we're only learning about the true value of that message, and we're only putting resources there. We're getting more confident about how good is this message. We're learning the value. Now, some other messages have like a very wide curve. And this curve is because we're not really certain about the true value of this message. But we know that in the best case scenario, it's never going to be as good as green in the worst case scenario. So we don't have to spend any more resources playing in this bad slot machine. We only want to play in the good slot machines. And here's the final product. This is how we find the best next message to the user. This is a screenshot from the game. This is the message that got selected to a user. So this is from Black Ops 4, last year's game. And we learned what are the best messages for this user. So the top message is to showcase next year's game, which is this year's game's Modern Warfare. And we have 2 engagement messages right after, and we have like a sales message after this.
Thank you, Diego. Is my mic working?
I think so.
Yeah, great. We walked through how we personalize individually for each gamer. Now, how do we scale that up to the millions of gamers that we have playing each and every day in Call of Duty? That is where we come in, and let's take a look at the actual architecture of how we make this run each and every day for all of our gamers. So starting off, we have, we source all of our data through a central data team through Kafka pipelines, and we have hundreds of thousands of events coming through the game each and every second. Hundreds of thousands of events. And we need to pick and choose which data is relevant to the models in order to make the decisions on what next best message we want to send to the user. So starting off with all of these data pipelines, we have applications that we call data pipeline readers. We have anywhere from 30 to 50 instances of these readers running at any time. They sit there, read the streams, and pick and choose, and they have 3 main functions. The first function is to store data raw into our NoSQL player data mart. Events such as platform or language, that gets stored directly into the database. Other events will trigger later on to be used for processing the users itself. And then lastly, the data gets put into the Kinesis streams in order to calculate the attribution like Diego was mentioning earlier. So I'll start there and look at the Kinesis streams. We have real-time Kinesis analytics attached to those streams using Lambda to pick and flow through the real-time analytics of the streams. The Lambda also triggers a custom application that we wrote that is a interface on top of Neptune, AWS Amazon Neptune database. It's a graph database that allows us to store each of these states of the users. And we have another application, the backpropagation, that actually does the learnings and stores that back into the database itself. Okay, so we have the database, we have the graph, we have the user states. So now we actually do the actual work. That is done through assignment workers. The assignment workers grab the data out of the data mart. They grab your state out of the Neptune database. They pull the content out of our CMS and are triggered by the real-time queues. They send the data through sender applications into the various channels, such as in-game messaging, email, SQS, SMS, whatever channel is decided to be used at that time for that action. So that's an overview of our architecture. There's a lot going on there, but that isn't the only applications that we support in our group. We have websites, APIs, all that good stuff. And in order to support all of these applications, the past few years, my team and I have been building a structured pipeline in order to handle the scaling, deployments, and making sure the developers have exactly what they need in order to deploy what they need when they need in a safe and structured manner. So we went all in on Docker and Amazon ECS, and we developed a framework that we call Raptor. Now, Raptor is a combination of two different sides of the house. First, we have the Raptor, the DevOps framework Git repository. It stores all of our Python scripts, all of the nuts and bolts of the pipeline itself. And then each application gets its own set of configuration files in order to tell Raptor what to do with the application and how to deploy it. These are combined in an automated build system. Most of you can probably assume what we use, but we won't say the name. The jobs do their thing. Raptor does its work, stores Docker images into ECR, deploys out to ECS, application load balancers, Route 53 entries, and whatever Amazon service we choose to integrate within our framework. We just did EFS volumes, so developers, if they need permanent storage in their applications, they're able to use an EFS mount in order to permanently store whatever their application needs. So that's an overview of the pipeline itself. So I want to walk you through what day-to-day, what it looks like for an engineer in order to use the pipeline and how easy it is for them to use it. So the engineer first, does their code and does their commit and pushes their code commit up into Git. And then we have Git commit hooks that actually triggers the build jobs, do the work, and build the Docker images, and push those images straight to ECR. Every single commit, every single push gets pushed up into ECR. Gets tagged with the Git tag, and is just sitting there waiting to be deployed. When it's ready to be deployed, an engineer chooses what tag, what branch they want to deploy, what environment they want to deploy, and clicks a little button in the build automation system. Then Raptor will generate a version number, an incremented version number. It is automatically done for the engineer. They don't need to even think about build numbers or version numbers. It's all done automatic behind the scenes based upon your branch and so like master branch, develop branch get a major number, and then feature branches get minor numbers. It's all automatic behind the scenes. And those tags automatically go up into ECR. The ECR image gets tagged, and the git commit, the actual git commit itself gets tagged with the version number. So the engineer can later look in their Git history and see a complete history of what versions were deployed. Lastly, Raptor will generate the appropriate CloudFormation templates and submit them through the CLI, and then monitors the progress ongoing in order to adjust for any failures or retries that it needs to happen. As we all know, CloudFormation is perfect. Yeah. So let's take a quick peek at what a a Raptor cluster configuration file looks like. So what we decided to do for our infrastructure is we've, instead of going for the monolithic clusters, for example, dev cluster, stage cluster, prod cluster, we decided to go the route of microclusters. So each application has its own cluster. Each application has its own environment cluster as well. So if you have 5 applications with 5 environments, you have 25 clusters. It adds up quick, but with the structured pipeline, we're able to manage it effectively and quite easily as well. This allows cluster isolation where one application won't impact another. Each application can decide whether they want to use spot instances or on-demand instances based upon their needs. For example, dev environments, don't be using on-demand instances for dev environments. Spot are just fine, and we could save some money doing that. Another fantastic thing this allows is automatic resource tagging. This is something that everyone struggles with. Does your EFS mount get tagged? Does your volume get tagged properly? Well, the structured pipeline allows us to put that programmatically in, and we don't need to worry about it ever again in the future. The next thing is we'll take a look at what a Raptor service configuration file is. So the service configuration is individual services within an application. An application can have multiple services to the cluster. It could have multiple containers in a service. The options are endless of what the engineer is intending to do with their application. You define custom alarms in here. So if you want your service to scale up, say, for an SQS queue or a custom metric within CloudWatch, you specify it within your service config, and that automatically gets added to the CloudFormation template itself, and the alarm gets added. You can specify one or many containers at a time. We all love Nginx sidecar containers, so we have the ability to do that, even though we kind of discourage that. But some applications do need those sidecars, and this allows it to be defined per service within a cluster. And lastly, environment variables automatically injected within the containers itself. So you define it at a service level, and you get them within your application level right then and there. And lastly, what this structured pipeline has allowed us to do is really support a really large scale infrastructure in terms of the number of applications we support. We have over 35 independent applications across 80 plus clusters, 5 primary environments. We have the dev, stage, QA, pre-prod, and prod. However, with the pipeline itself, a developer or an engineer can define their own environment if they want. We could have a Bob environment, we could have a Joe environment. The options are endless. They spin up and spin down, all without anyone going into AWS console. It's all within the code. We have over 200 spot instances that we run, and with less than 50 on-demand and reserved instances, as the static systems will, the Jenkins and the Git servers, we want to keep those as reliable as possible. But the dev environments, the stage environments, we spin those up and down at will, and Spot does really great on that. And the structured pipeline that we've been able to build really enabled this to scale this machine learning model from one player to many.
So you've heard a little bit about what we did, and now you're probably wondering, did it work? This is definitely the question that the business asks us. And the answer is yes. So moving away from our traditional rules-based approach resulted in more hours played per user. The slide before you shows where we started and where we are today. When we started this process, going with machine learning, from the beginning, it outperformed our historical rules-based approach and our control group. And over time, our machine learning model was much more effective at choosing the messages to nudge players to those new states. and that gap in hours played only increased. And most importantly is that this did not come at the expense of what the players were already doing in our games. The increase in hours played came from players exploring new parts of the game and experiencing new features. But this wasn't the only thing that we learned. There were 4 other key things that we learned from our players. First, there was a group of players that had played all the previous COD titles. And so messages that touched on things from previous Call of Duty titles that were in our current game were really relevant and really connected with those players. They loved hearing about how a section in Blackout was in their favorite Black Ops game. We also learned that that rule that we created early on that said only players that play 1 hour of zombies should see zombies messages was right. We learned that was our gut, that's what we thought, and our gut was wrong. It turns out that there are a big group of players out there that want to hear about all parts of the game. They may not always play it, but they want to know. We also learned that that old saying, if you don't have anything nice to say, don't say anything at all, holds true here. So there were times when we didn't have anything good to say to the players. From that pool of messages, those messages that were available, there wasn't a good option. So we were better off just not saying anything. In those instances, we would flag that and then figure out what was missing from our pool of messages that we should be talking about. And then finally, we needed a lot of messages. And when I say a lot of messages, I'm not just talking about I'm not talking about creating a lot of messages about a lot of things. I'm also talking about creating a variety of messages about the same thing. Not everybody looks at your feature and your product in the same way. So you shouldn't talk about that feature to everyone in the same way. So as we wrap up, I know you're probably thinking, is this really worth it? This kind of might seem like a lot of overkill to target messages. Wouldn't it be easier if I just created 10 segments for my customers and just focused on those 10 segments? Because this was a lot of math and a lot of infrastructure. And you know what? We asked ourselves those same questions. But then as we were talking about it, and I would think, if we came up with 10 segments, what segment would I be in? I'd probably be in the casual Call of Duty player. But then who else would be in that segment with me? And when I looked around at those people in that bucket with me, I realized that while we all may be casual players, I'm not the same as that person, and I'm not the same as that person. They are actually good at the game, and I am a terrible player. So talking to me about the same things as you would talk to those players was not going to have the same results. So if our goal is to connect players with the features that matter to them in a way that matters to them, just as you want to connect your customers to the features that matter to them, the only thing that you can consider, for us, the only thing that we could consider and the best solution was to create just a segment of 1. Thank you. Whoops.